Anyways, everybody, I want to give you a little bit of a recap from where we were last time. So last time we described Kleine's theorem. This is how I characterized it, is that a language L is regular if and only if there is a regular expression that describes L. Now, the way we defined a regular expression last time in our previous lectures, we described that we call the language regular if there existed a deterministic finite automaton that recognizes said language, right? Well, we had these working parts. So to prove this claim, we had a couple moving parts, right? So last time we had actually established that I could give you a regular expression and I could show you how to build an equivalent epsilon NFA. So we used Thompson's construction to be able to do this. That was the key part of the proof. Previous to this, we have actually also seen how to take an epsilon NFA and build a corresponding DFA. That means that if I give you an epsilon NFA that recognizes some language L, then this DFA that you get as a result of the construction, namely in this case the lazy subset construction, you get a deterministic finite automaton that recognizes L, so the same language. Now there's one key part that's missing here, because if I wanted to establish this claim, well, one way I can go about it is notice that for one direction of the proof, we've actually established one direction of this proof already, right? We've established that, what did we establish? That if there's a regular expression that describes L, then it's regular, right? Because notice that I could give you a regular expression, I could build an epsilon NFA corresponding to its language that it describes, and I could also transform that into a DFA. Bing bang, nice, right? But now we have to establish the other direction. Now, the way we're going to be doing that here is we're going to be given a DFA. I'm going to show you how to build a corresponding regular expression that describes the language that this DFA recognizes. And once we've established that, we end up with this claim right here. And we get a whole bunch of free stuff as a result of that. So that's actually why I held off on some of the claims. We're going to talk about that more afterwards. So to make this all work and easier for me to describe to you the claim, I'm going to suppose without loss of generality that a DFA has states that are going to be 1, 2, all the way up to n, where n is the number of states. So you might be wondering, what do you mean by without loss of generality? It means I can do this with any DFA. This is just a simplifying assumption. So I could make this claim, so I'm going to prove it using this, but notice that I could do this to any DFA, right? I could just relabel the states so that they're like this. And the argument I'm going to present to you, it doesn't make any difference how those states are labeled, they're going to look like this. But it's going to be easier for me to describe it in the way I'm going to here shortly. Now, you might be staring at how we've done all of our other techniques for proving equivalencies, and you notice that we use mathematical induction a lot. Now, previously we had actually used Thompson's construction, which used structural induction, and we built successively larger epsilon NFAs from successively larger sub-expressions of the regular expression. So notice that in that case, it's that I'm taking this regular expression, I'm building up to the whole thing, right? And I get a corresponding epsilon NFA. But in equivalence proofs that we've also seen, we've also performed induction on the length of the string. So you're going to see at first, it's going to be a little bit, we've actually seen at least a couple other ways we could establish the equivalencies between corresponding models of computation, or in this case, ways to describe a language. We're going to be using another one, and I need you to follow me very carefully when we do this. So we're going to be using the concept that we're going to refer to as a k-path. And it's going to play a very large role in relation to how the states are labeled. So this at first is going to look a little weird if you've never seen this before. So please just be patient and let's just walk through it carefully. Because at first the intuition for why we would consider one of these k-paths and perform induction over k is going to be not as obvious at first. So here's the definition we're going to have for a k-path. So what does it mean? And now remember, as I've discussed previously, I'm going to be using graph theoretic terminology in place of automata-based terminology. So for example, when I talk about a pathway, I'm talking about a sequence of transitions. Likewise, when I talk about a vertex, I'm talking about a state. And when I talk about a transition, I'm talking about a directed edge or arc. So I'll use that phrasing often interchangeably when we discuss this as a matter of intuition, but also you could easily replace with that terminology as well. So what is a k-path? Is where every vertex contained in this path has a label, meaning that's the label of the state, is at most k. So if I ask for a 2 path, it has to be that every vertex contained along the path has to have at most 2 for its label, except for 2, namely the ends of the pathway. So those are allowed to be whatever you want, and that's actually going to be fairly important for us. So here's the intuition here. If I give you some k-path, imagine this is the start of the path, this is the end of the path. I don't care about what states these ends of the pathway are labeled as. I care about what's going on in between here. So these are what we were going to refer to as intermediate vertices or intermediate states. So these ones all along this pathway, not on the ends, have to have a label that is at most k. So please keep that in mind. It sounds like a very small, delicate detail, and in fact it is, but it's also a technically important detail. So please don't forget about that. So another piece of simplifications I'm going to make for the discussion we're going to have. Otherwise it gets very verbose. I know even adding the word very makes it more verbose. It makes it more verbose for what I want to describe to you. So I'm going to give you the concept of a label of a path. So if I give you a path, it's simply going to be the labels of the arcs or transitions that are in that path. So you know how when we have, for example, a DFA, and I give you a string, each string, when I read symbol by symbol, it dictates the transitions from one state to another state. So those are what I'm referring to here, is that these are the labels of the arcs or transitions. So when you each one of the symbols, it's just like if I'm reading off the transitions on those directed edges or transitions. So what this is going to correspond to is the string used the transition from the start of that pathway to the end point of that path. So just imagine it, here's the intuition. Just imagine it's like you're reading, you have the machine, you're in a given state, that's your start point. You read off some of the symbols that are in this string. If you read off that string, the label would be the transitions. So what those labels for the transitions are that take you from one state to the next. So you'll notice that that's actually a sequence. So these are going to be the labels of those transitions, which naturally are what you see in the input string, correct? So that being said, let's do an example so that way you could see what I'm talking about when we talk about a k-path. For this example, we're going to use this example quite intimately. So please, I suggest if you're going to doodle this somewhere it's very easy for you to come back to it. So it's going to have 2 states. So the start state is going to be state 1, and the final state is going to be state 2. And we're going to have a loop that keeps me at state 1 if I read a 0. And to go from state 1 to state 2, I read a 1. So I transition on 1. But once you're in state 2, you stay in state 2. So you imagine the input symbols here are 0 or 1, right? So just binary. So let's talk about what the k-paths would be in relation to a path from 1 to 2, because notice that this is the start state, that's the final or accepting state. So here is the intuition behind this. So well, at least this is one way you can think about it. Using k-paths, we can describe strings accepted by a DFA. Via a regular expression. So let me give you some examples of what I'm referring to. So notice that the start state, as I mentioned, is state 1. The final or accepting state is state 2. So I'm going to describe paths that go from 1 to 2. So I'm going to use this notion of the k paths. So we're going to try different values of k and see what happens. So let's consider all 0 paths from 1 to 2. So from state 1 to state 2. So what I want to do is I want to consider all 0 paths that get me from 1 to 2, from state 1 to state 2. And I want to describe this as a regular expression. So now we're not quite at the stage for which we're going to see how k paths relate directly with the idea, but I want to show you that you can matter-of-fact describe regular expressions for these k paths. So we're going to consider all 0 paths from 1 to 2. So what is a 0 path? Let's start off with that. So what would a 0 path look like? So we're going from 1 to 2. So imagine you have state 1, state 2. Now, the first thing you should notice is that 0 path. So anything in here, any states that we were to transition along this pathway, which might I stress, may have repeated vertices in it, meaning their labels are the exact same. All of the ones in between here can be at most 0, but we're allowed to have the 2, we're allowed to have the 1. So it means that if you actually think about it, all of the 0 paths must go directly from 1 to 2. Why? It's because every one of the states is labeled 1 or higher. Does everybody see that? So let's look at our example over here. Let's see how can we get from state 1 to state 2 without using any intermediate vertices. That's what this means, because all the states over there are labeled 1 or higher. So to go directly from state 1 to state 2, what would be the regular expression that describes all strings that take me from state 1 to state 2? What would it look like? Well, you see there's only really one, right? There's only one 0 path that exists here, right? From 1 to 2. To go from 1 to 2, I have to read a single 1, right? So what would the regular expression look like for all 0 paths from 1 to 2? Well, it's just the regular expression for 1, right? Because I go directly from 1 to 2. I'm not allowed to take any other states along with me along this pathway. I'm not allowed to even reuse the states. So let's consider all 1 paths now from 1 to 2. So what is this going to look like? So the intuition here, so remember this is kind of the big idea, is that remember, I'm allowed to have 1, I'm allowed to have 2 for free. But any states that I transition to along this pathway, which might repeat vertices, by the way, like I said, they're allowed to be at most 1. So if you keep that in mind, that means that you're actually allowed to repeat on state 1. If you see that right away, then you got the idea of what a 1 path would be. Because notice that my path, which would correspond to the string which I read for that given one, notice that if I go from state 1 to 1, and then I go to 2, notice that every one of the labels that are along the middle, the intermediate vertices or intermediate states, they're all at most 1. So I'm allowed to go to state 1 as many times as I like, then go to state 2. So if you keep that in mind, that means that I can stay over at state 1 as long as I like, effectively. So I can go there no times, I can go there 1 time, I can go there 2 times. So each one of the 1 paths corresponds to each one of those. So there exists a 1 path that takes me directly from 1 to 2. There's one that goes through this self loop here back to 1, then goes to 2. Then there's one where it goes twice and goes to 2, goes 3 times, then goes to 2, and so on. Well, let's think about what that means then. That means that I can go on state 1, I could go revisit 1 0 or more times, right? But how do I transition in 1? Well, I could read a 0, right? So I take 0, and I apply star to it, that gives me 0 or more, right? Then I have to go from state 1 to state 2. That's why, considering one path from 1 to 2, then I have a 1 that takes me from 1 to 2. Notice that I cannot do any transitions once I've reached 2, because notice that the label for that end state is 2. It's greater than 1. So remember, I get the starts and the ends for free, right? I get the start and end for free. It's what matters in between here. That's what matters. So let's consider now all 2 paths. So hopefully you're getting the idea here. Let's consider all the 2 paths. So what does this look like? Well, if I consider the states that are going to go along this, it has to be that all of the labels of the states have to be no more than 2. But notice every state here is at most 2. But notice that, that if I want to go from 1 to 2, notice that now I can do this 0 or more times. Then I go over to 2, and now I can stay in state 2 as long as I like on 0 or 1. So you see how I can write this out as a regular expression? So I take the same idea I had here. This will get me over to state 2. Then once I'm in state 2, I can continue on 0 or 1, right? And I can do that 0 many more times. And this would actually correspond to all possible 2 paths from 1 to 2. But here's the kicker. Here's the kicker. Do you notice that any one of the strings that gets me and stays in this accepting state upon reading the string for my DFA actually looks like this? So this is actually describing those strings. So I'm going to make a note about that. So notice all strings accepted by the DFA correspond to the labels of, how many states are there in this? There's 2 of them, right? But 2 is n in this case. Of n paths from state 1 to state 2. Notice that there's no more than n states, right? So they can't consider more states beyond n, because there's n states, right? And to consider all possible pathways means I need to consider all possible states, right? So there might be other pathways that get me from the start to the end. I might encompass all of them without considering all the states. But to be sure that I've done this for every one of the states, I need to consider all of them, right? I can't just partially consider half of them unless I knew for certain that they have nothing to do with a string being accepted by the DFA, correct? So here's the intuition behind this. Do you notice how when I consider the 0 paths, I got one element of what I had here, right? Do you see how I have the 1 over there? Notice when I consider all 1 paths, it gives me this ability to stay over here at 1, then go over to 2. But for all the 2 paths, notice that it takes me and gives me a description as a regular expression, all of the strings that would be accepted by the DFA. And naturally, this is a regular expression, well, that is, for the language that would be the one that gets recognized by the DFA. So let's talk about the intuition behind this then, because I'm going to be showing you how to build this regular expression. So here's the idea that we're going to try pulling out. So we're going to inductively build, a collection of regular expressions that describe broader and broader sets of k-paths of a DFAD by increasing k is equal to 0, 1, 2, all the way up to n. Remember, we need to make sure we've encompassed all the states, right? There might be some pathway we don't account for if we don't go all the way up to n, at least for an arbitrary DFA. So what we're going to do is our proof is going to use induction on k. Which, at first, this will look a little strange because we're used to performing induction on, structurally at least, the number of states. But notice that I'm using it now in relation to this idea of a k-path. So notice that when k is equal to n, there are no states greater than k. And if you actually think about it carefully, do you notice that how k actually imposes restrictions on the types of paths we can get? Well, if we allow k to be equal, in fact, to the number of states, then it must be unrestricted, meaning that there is nothing preventing a pathway from getting from one state to another state in our definition, should it exist. Meaning that the paths considered are unrestricted. Now there's another kicker here. Fortunately for us, we know what the final states are for a DFA. That's a part of its definition. So if we know that, then most certainly we can also take into account which states are indeed the final states. So let's make a note about that. Furthermore, if we were to take and sum / union together, because remember, for a regular expression, we have the union operation, right? We're allowed to have that. Union together all regular expressions representing n paths from the start state to each final state of D. Once we can do this, we've captured all of them, right? Furthermore, if we were to take and sum or / union together all regular expressions representing n paths from the start state to each final state of D, we can capture, I'm using this in a fun exploring kind of phrasing, we can capture as in describe or specify, capture all strings of language L of D, right? The language of the DFA. So this is going to be the big part of how this proof is going to work. And I would argue that the construction reveals a rather interesting structural aspect of regular languages that we'll actually see potentially in future lectures. So here's the theorem that we're going to be proving here today. Here's the theorem. If language If language L is equal to the language of D for DFAD, then there is a regular expression R such that L is equal to the language of that expression. So this is what we're going to be proving. We're going to use mathematical induction. We're going to perform induction on K in relation to this concept of the K path. So check this out. Check this out. My eraser just about blew up on me. So let's do the setup for the proof. So let's put all this formalization in place. So suppose language L is equal to L of D for some DFAD. For some DFAD, where its states are labeled 1, 2, all the way up to n, where n is the number of states. And note that we could do this with any DFA. Now, I'm going to be throwing some technical jargon at you, so I'm going to decipher it for you carefully. And we're going to go through this very carefully. And it will actually see that it's very much the same idea we just talked about a moment ago when we were doing our examples with the K paths. So let R sub ij with superscript in parentheses K be the name of a regular expression whose language contains the strings W, so that W is the label, and just to be clarifying with you, as we described earlier, this is all transitions read along the path. Is the label of a K path from state I to state j in D. So now, if you actually look at this carefully, what actually this notation means is, you know how we talked about like the 1, 2 paths? So the paths that go from 1 to 2, like in our example, that's I and j here. And k, denoted here, will be what the k value would be for the k path. So for example, we talked about 0 paths, 1 paths, and 2 paths for our DFA. That's what k is right here. It's going to feel like we're going to be creating rounds of successively larger regular expressions on k. So you're going to think of this superscript here kind of like a round for which it's going to generate the successively larger regular expression that's going to be taking aspects of the previous types of paths where k is 1 less and appending or creating the one for which it is k. That's how it's going to work with the induction. So now with the setup here, let us perform induction on k. To define Rij superscript k. K is equal to 0, 1, all the way up to n. So we're going to use this to prove our claim. So similar to my first part of Kleine's theorem, I'm going to put and embed the argument for how this construction is in fact correct in the explanation I provide you. Sorry, I get really excited here. I'm just losing it. So let's start off with the bases for the construction. So this would be when k is equal to 0, just to be very clear. I'll add that in here. So all states, so what would happen with the k paths here? Well, there's 0 paths. And what did we establish earlier in our discussion when we considered the 0 paths? That there aren't any intermediate vertices, correct? There are no intermediate vertices or intermediate states, what we've described before, right? So it means you're going to go directly from I to j. So this is going to be where all the states are labeled 1 or greater. 1 or greater. 1 or greater. So any 0 path contains no intermediate vertices or states. So that leaves us actually with only 2 possibilities that can happen, right? It could be the case that you go from the state that you're currently in and you stay in your current state, right? Or it could be that you go from one state to a different state with 2 different numbers for their labels. So observe that there are 2 possibilities. For our claim, right? Again, it's very excited here. That R there, let me fix that R. It's looking a little bit too close with that U here. So let's consider the 2 cases over here. So the first case I'm going to consider is when I is not equal to j. So that means that there's an arc from state/vertex I to state/vertex j. So now, to make this happen, let's consider all possibilities that can occur in this situation. Then we consider D and find symbols, specifically input symbols, symbols A, where there is a transition from I to j on A. So I'm also going to include the possibility that there is no symbol. Suppose that there is no symbol that takes you in this case. So if there is no symbol A that takes you from state I to state j on A, so if there is no symbol that is capable of doing this, so this is when you just don't have a transition on that given symbol from I to j. If there is no symbol A as above, then we could define it as follows. Then Rij 0 is going to be the regular expression for the empty language. If there is, so you just imagine your DFA, there isn't a way you could go on symbol A from I to j. then that would be what you would include for that case. How about if there's one symbol? So this would be the case when you have no way, there is no symbol to go from I to j. Suppose that there is one symbol that gets you from I to j. So if you had this symbol, you could transition from state I to state j. If there is one symbol, A, then we can define it like this. Then Rij superscript 0 is going to be the regular expression on symbol A. Naturally, if I have multiple symbols, what is that going to look like? So if there are symbols A1, A2, all the way up to AK that have arcs, or they're just labeled on the same transition, arcs from I to j, then naturally we could just do the same idea we had in case B here. Rij 0 is going to be the regular expression where you include the regular expression for symbol A1, the regular expression for symbol A2, and so on, where I'm just going to perform union operation among all k of them. So, do you see how you can easily modify this if you wanted to include other things? But I'll let you think about it. So let's consider the other possibility for the bases. This is when I is equal to j. Then the zero path contains only some state or vertex I. So what does that look like if I want to go from I to I? Well, you can even watch it with my finger, right? That means it's going to look like a self loop, right? It's probably going to look something like that. Right, Miss Katie? Yeah, she agrees with us. So let's see how this goes. So observe, right, Miss Katie? I haven't forgotten about it, Miss Katie. Don't worry. Observe that if a transition on symbol A exists, it will be a self loop. So what does that mean then? That means that there's going to be an option to take the self loop. As soon as you see it as an option, what does that give you as an intuition for what the regular expression should include? It should include epsilon, probably, right? Then exclude expression epsilon with each of the above cases. So just to be very clear what I'm referring to here, what I'm saying is for this situation, what you would do is you would have each one of these, so have no symbol, one symbol, multiple symbols. So what I'm saying is just union with epsilon. And do note that this actually equals this expression. Remember, this is the empty language, that is the set containing the empty string. That means that if you take the union of the two, then you're just going to end up with this for the regular expression. Same idea here, you would just union that with the empty strings regular expression, right? You do that for each one of these cases. That's what I'm referring to here. So just to summarize what these two cases look like, case 1 looks like this. Or if you have a transition from I to J on A, B, or C, then what is that going to look like? Well, it'll look like an expression that looks like this. And in case 2, you're going to have a self loop that goes from I to I or J to J, however you'd like to describe it. So this is just the same thing, except I include epsilon. And those are the two cases that correspond to these two. So please take note that these inclusions that I have here, those are specifically for case 2. So if you want to go through the exercise of writing out these 3 cases, I encourage you to do it with these new forms. So that leaves us now, since you can clearly see quite nicely that each of these describes how I go from I to J without using any intermediate vertices, right? Let's see what happens if we want to take this to the next round, for an arbitrary round from one round to the next round. Let's consider the induction aspect of the construction. So assume there is a k path, P, from state I to state J. So suppose that I have this. Now, what we're going to do now is we're going to presume this as the induction hypothesis. So imagine I have a k path from I to J. So it means that I know what this looks like. So that's going to be our description of the regular expression, right? So that's what the name of it is. So then we're going to see that this is going to have a nice property, because now what I want to do is I want to see how this is going to work when I go from one step to the next step. So then there are 2 possibilities. So you can, of course, go from state I to state J, right? And you could do it without visiting a state for which has label k, right? You could be that possibility. Remember back to when we were talking about a k path. So you know how I had state I, state J. These I'm allowed to have for free, but in between here, it could be the case that the label may be smaller than k. It may be k, right? So one possibility is that in between here, there's no state k. No state k. State k doesn't appear. However, in another possibility, state k could appear here, but it may appear 0 or more times. So that's how we're going to come back to our definition here. So it's going to break into the 2 nice cases here for how we can describe this as a regular expression. So P never goes through state K. So what does that look like? Well, let's kind of do a doodle like we had before. Remember, this isn't part of the proof. This is just a side doodle to help us understand. So it would be I and J. I go through stuff, right? But it doesn't go through state K at all. So what would it look like if I wanted to consider this one right here? What would this look like in this case? What would that look like? Well, if it doesn't include K, then it must be that every one of the intermediate labels has to be less than K, right? then the string corresponding to the label of P is in the language of what? What would be the language? Well, let's use our notation here. You know it's going to be from R, it goes I to J, right? But none of the labels are going to be K, right? So they're all going to be less than K. So it means that in this situation, the regular expression I would get as a result will be exactly this one. And since we already know that this will have such a K path that exists, that naturally means that in this situation that we've actually also have an expression for Rk minus 1 ij. So this is us using the fact that we know how to build this, presumably, for some round that came just before this one. So remember, we're considering round K now. So we're using induction here to find how we can decompose this into the smaller values of K. Remember, we're using induction on K. I want to show you how you can take the previous step to build the current step with value K. So this is one possibility. The other possibility, remember, if P never goes through state K, that means the other possibility is that P goes through state K. But it may do it multiple times, right? So so this is what P would look like. There's only two possibilities for P. So assuming that this does exist, then it has to look like this, right? It's going to have, goes through, state K. How many times? Well, if it goes through no times, right, then most certainly that's the first case. So it means it has to go through one or more times. So what's that going to look like then? What's it going to look like? Let's think about this. So if I want to come up with the expression for this K path, I'm going to need to think about this very carefully. So check this out. So here's what this is going to look like. So using an idea like we had with our doodle here, I could go from I to J, right? But you know it's going to go to state K at some point, right? Goes to state K at some point, right? Then it could potentially go and revisit state K several times, right? Maybe multiple times, possibly. Then it will go from K to J, because it has to pass through K at least once. Because if it didn't, it will just simply be case 1, right? But do you notice how there's actually 3 parts to what I've just described to you here? There's 3 parts. There's this part, there's this part, and then there's the part from K to J. So let's describe what that is, and we'll see how you actually get Rij for a value K from a previous round. So check this out. So notice that the label of P can be decomposed into 3 parts. Based on states I, K, and J, right? So you could go from I to K, then you might be K to K, one or more times, then what? Then you can go from k to j. There's 3 parts to this. So you have this one, and this one. I'll put more of the details in the notes about each one of these cases. I just say them orally. But what would each one of these be as a regular expression? What would each one of them be? So for going from I to k, I do that once, right? So what is that expression? Well, it's r I k or k minus 1, right? Because remember back to our definition of a k path. You remember, the ends don't matter. It's what matters is in between. So notice that every one of the labels between here and there has to be less than k. So most certainly, if you compute all of the values for k minus 1, you most certainly can get this right here. So because of the inductive property that we're using here, this has to exist. Because we know how to do it for k minus 1 paths, right? Okay, how about the second part? Second part. So it passes through from k to k. Now please note that it goes from k to k, but it could be that it's just I, k, j, right? So that means it may pass through k, meaning it comes and repeats on k 0 times, right? It could go 0, it could go from I, k, right to j, or it could be that it repeats k once, k twice, and so on. So once it reaches k, it may be the case that you don't actually revisit k again, right? So in this situation, let's think about that. You're going from state k to state k. So similar to the case that we had before, except now, remember, I don't necessarily know at this stage what this is, but I most certainly know it exists because of the inductive, like if we presume the induction hypothesis. So I'm presuming that this exists because I would have had to have computed it up to this point. But notice that that is describing it so that I can go from k to k, where I can go from k to k, but notice that because of our definition, it goes k to k, but notice it doesn't, we don't care about the ends, right? So that's why I've included k minus 1 there. So I can go from k to k, and I'm allowed to do it this way because the ends of the path they don't matter, right? But remember, I might do this 0 or more times. So, because I'll go from I to k, and then go k to j, right? But I might not use this k to k business any number of times. So I'm going to put a star on this, which means 0 or more, right? Because this gets me to state k. This allows me to repeat on state k, and then that will allow me to go to the other ones. But remember, take note that it might, if it goes from k to k, it's going to be on labels that are going to be less than k if they're intermediate ones, right? What about this last part? Well, it's similar to this one over here, right? Well, it's going to be r, k, j. But again, by the same reasoning that I gave you, this one right here, all the intermediate labels, all of the intermediate states that you would visit. I should say states to be a bit more precise. All of those ones are going to be less than k, right? Because remember, by our definition, remember, the ends don't matter. It's what's in between here. And we already know how to build that, presumably because I have had to have computed this for a previous round. So you got to imagine it like I'm doing this round by round for increasing values of k. So what can I do now to capture this case? What can I do? What is this nice thing we have for regular expressions? Well, so how can I capture, actually, let's do it even better. How do I capture this one? So what would this look like? Well, it most certainly will just be a concatenation of these three, right? So you take the concatenation of all three. So you concatenate all of this in that order. And that's case 2. So how do we actually describe this for round K then? Well, look, I have this situation and I have that one over there. It's one or the other. What operation do we have for that? Or. Union, right? Hence, by applying union for the two cases, because these are our two possibilities, right? Here's what we get for RIK. So Rij for value k. Well, it's the first possibility, right? Rij for round k minus 1. Or, so I'm using this union, Rik k minus 1. Concatenate this with the version with the star, where we go from k to k. And then last we append this third part. Rkj k minus 1. Here's some important remarks. So to compute Rkij, we rely on computing expressions for smaller superscripts. So for smaller values of k. Or superscripts. So you start at 0, you work your way up to 1, then you work your way up to 2, and so on. Let me see here. I just want to make sure I don't get too ahead of myself. Superscripts. Then from k is equal to 0, all expressions can be made available to compute the expression Rij k for any k is equal to 0, 1, 2, all the way up to n. As I've already remarked previously, if I actually want to get the final expression when I'm done, let me just summarize how that works. So that's just a remark. So now let's finish up the proof. Notice that for k is equal to n, we can compute as described above. So in the remark, Rij superscript n for all I and j, assuming that state 1 is the start state. So this is just, if I make 1 the start state, it's easy enough to do that when you're labeling the states. Assuming state 1 is the start state, then observe, this is by the construction. So remember, when I was describing this induction part, I was showing you how to build for round k the expressions given that k minus 1, this one for the superscript when k minus 1 is the case, i.e. when we have k minus 1 paths. So all now I'm doing is pointing at that construction and saying, hey, look, it has this property. Isn't that neat? So, and then that's how we're going to finish this up. Because I already gave you the reasoning for why these are the two possibilities that can happen. So then observe that the regular expression, for L of D, remember D is the DFA, is the union or sum of all expressions R1j superscript n, where j is an accepting state, or final state, however you'd like to phrase this. And that finishes up the proof. So now we've described how you can build a regular expression from a DFA through successively increasing the value of k in relation to a k path. And I show you how you go from a k minus 1 path to a k path, as in if I give you the regular expression for k minus 1 paths, then I can show you how you can build the regular expression for a k path. And by the way we've constructed it carefully, we're able to figure out what expression would actually be the one that we'd be interested in, or the multiple ones if we have to perform a union operation if there's multiple final states. So that completes the proof that we needed for Kleine's theorem.